Today we discuss the topic subgroup. G star is a group and H subset of G, and star is a binary operation on H also, then H star is a subgroup of G. That is, if H star is a subgroup, then H star itself is a group. Okay, and H is a subset of G, and the operations are same to both H and G. Then H star is a subgroup of G. We know that Z under addition is a group. Okay. R under addition is also a group. Also, Z is a subset of R. So, Z under addition is a subgroup of R under addition. Similarly, Q star under multiplication. Q star means set of all non-zero rational numbers. That is 0 excluded from the set of rational numbers. That is Q star. So Q star under multiplication is a group. Also R star under multiplication is a group. R star means set of all non-zero reals. So R star under multiplication is also a group. Here Q star is a subset of R star. Therefore, Q star under multiplication is a subgroup of R star under multiplication. Next example, Q plus under multiplication is not a subgroup of R under addition. Here, Q plus means set of all positive rational numbers. Set of all positive rational numbers is a subset of set of all real numbers. Here, Q plus is a subset of R, but the operations are not same. Operations are different. Here, multiplication, and here it is addition. So, Q plus under multiplication is not a subgroup of R under addition. The subgroup exists only when the subset, the operation defined on the subset induced by the operation defined on the superset. Okay. Now, proper and trivial subgroups. If G is a group, G itself is a subgroup, like set. H is a set, H itself is a set. Like here also, if G is a group, then G itself is a subgroup. And is the improper subgroup of G. Okay. G is known as improper subgroup of G itself. All other subgroups are proper subgroups. Okay. The subgroup set identity, that is trivial subgroup. Okay. A set with a null set is a trivial set. Like here also, the subgroup set E is the trivial subgroup of G. All other subgroups are non-trivial subgroups. Okay. Also, another example, the multiplicative group 1 minus 1 is a subgroup of the multiplicative group 1 minus 1 I minus I. First we check set 1 minus 1 under the operation multiplication is a group or not. 1 minus 1, 1 minus 1 operate under the operation multiplication. 1 into 1, 1, 1 into minus 1, minus 1, minus 1 into 1, minus 1, minus 1 into minus 1, 1. Here this operation is binary. Also it is associative. Also an identity element exists because 1 is the identity element. If we in all the rows 1 exists, 1 into 1 is 1. Minus 1 into 1 is minus 1. Okay, minus 1 into 1 is minus 1. So 1 is the identity element of this group. And also every element has an inverse. Inverse of 1. What is the inverse of 1? 1 itself, because 1 into 1 is 1. So the identity element 1 get when 1 multiplied by 1. So inverse of 1 is 1 and inverse of minus 1 is also minus 1 because minus 1 into minus 1 is 1. So all the properties of the group satisfies. Therefore, 1 minus 1 under the operation multiplication is a group. Similarly, 1 minus 1 I minus I under the operation multiplication is a group or not. Here I the complex number. So 1 into 1, 1 into minus 1, minus 1. Similarly, I into I minus 1, I into minus I 1, and we fill the table like this. Here also multiplication is a binary operation and also it is associative. Also an identity element 1 exists because 1 into 1 equals 1 into 1 equals 1, minus 1 into 1 equals minus 1, 1 I into minus 1 equals I, and minus I into 1 equals minus I. Therefore, this also a group and every element has an inverse. Inverse of 1, which one is the inverse of 1? 1 itself, because 1 into 1 is equal to its identity element 1. Minus 1 into minus 1 gives the identity element. So inverse of minus 1 is minus 1. I into minus I is 1. So inverse of I is minus I. And minus I into I equals 1. So inverse of minus I is I. So these two are groups, and also first one is a subgroup of the second one. That's our example. The multiplicative group 1 minus 1 is a subgroup of the multiplicative group 1 minus 1 I minus I. Also another example, the additive group of even integers. The additive group of even integers is also a subgroup of group of integers. Next we discuss two types of group structures of order 4. Two types of group structures of order 4. A group with order 4 means that group has 4 elements. Okay. Number of elements in the group is its order. Z4 is a order 4 group. We know that elements in Z4 are 0, 1, 2, 3. We make the group structure like this. Here the operation is addition modulo 4. So 0 plus 0, 0, 0 plus 3 is 3, 1 plus 0, 1, 1 plus 3, 1 plus 3 is 4. What is 4 modulo 4? It is 0. So we get 0. Here also 2 plus 1, 3, 2 plus 2, 4. 4 addition modulo 4 is 0. Here 2 plus 3 is 5. 5 is congruent to 1 modulo 4. 5 is congruent to 1 modulo 4. So here we get 1. Like this we fill the table. This is a binary operation. Addition modulo 4 is a binary operation. Also it is associative. Also the identity element is 0. And what's the inverse? Inverse of 1 is 3. Here inverse of 0. 0 is the identity element. The inverse of identity element is always itself. And what is the inverse of 1? Here 1 operate with a 3, we get the identity element. So 1 inverse is 3. What is the inverse of 2? 2 plus 2 is 0. So 2 inverse is 2 itself. Inverse of 2 is 2 itself. What is the inverse of 3? 3 plus 1 is 0. So inverse of 3 is 1. Okay. Next group of order 4 is represented as V. It is known as Klein 4 group. Klein 4 group is defined as, here the operation is defined, not the usual multiplication. Here the operation is defined as E star E is equal to E, E star A is equal to A, E star B is equal to B, E star C is equal to C. Also, A star B is equal to C, and A star C is equal to B, and B star A is equal to C. Okay, here the operation is A star E is equal to A star B is equal to, here the operation is defined as E star E is equal to E star A is equal to A star B is equal to C, E star B is equal to B star C is equal to E star C is equal to C, A star C is equal to B. Here also we can check this is a group, it is associative and the identity element is E, and what is the inverse of A, B, C? Inverse of A is A itself, A into A is identity, and inverse of B is B itself because B into B is identity, and inverse of C is C into C is identity. Also you check, is it an abelian group also?